Okay, so today we're going to talk about convolutional neural networks. Since we haven't talked about it yet in this course, it's relevant for your second assignment. So hopefully, if you understand this tutorial well, it will really help you do the second assignment. And it's good to know anyway, because this is one of the major kind of forms of deep learning. So we're going to cover convolutional and pooling layers. We're going to talk about different architectures of convolutional networks. We're going to talk about how to do fully convolutional networks, which don't contain any fully connected layers, and residual networks, which is a kind of a new, better architecture. Okay. So very, very quickly, I don't want to spend too much time on this because we have a lot to cover. But let's remind ourselves what MLPs are and how they work, because we're going to need it. So again, an MLP is a model where you have multiple layers. Here, all the layers are the blue. This is a layer, okay? Each layer has multiple perceptrons or artificial neurons. So a layer has multiple, you can think about multiple inputs and multiple outputs. So this last layer, for example, has 3 outputs. And generally an MLP has some number of layers, which are hidden layers, and finally you get an output layer, okay? And briefly, if you remember what the equations look like, what each layer calculates is kind of this linear affine transform, which takes the outputs of the previous layer, multiplies it by some matrix, and this encompasses all the neurons in the layer. Okay, so if you have, I'll just draw it here for later. So this is what an MLP looks like. Each neuron is connected to all the inputs. Okay, it's fully connected, and has one output. So you can think about this matrix. It has rows that correspond. Each row in the matrix is the weights for each neuron. Okay, so you take all the inputs times the weights of the neuron, and you get one output. And you have a bias term, of course, for each neuron, and you have some kind of nonlinearity, as we saw, can be sigmoid function, ReLU, tan H. Okay. Now the full MLP is a construction of applying the same kind of transform multiple times, L times in this case with different parameters, as we saw, and as we talked about in the lectures. It's a very potent hypothesis class. There's a theorem that states that if you have even just 2 hidden layers, you can approximate almost any function if you have enough neurons, of course. Okay. So quickly, I'm not going to talk about regression. To explore conv-nets, we'll focus mainly on the task of image classification. So briefly remind yourselves that for classification, what you do is you take the output layer. Let's say this is the last layer of an NLP, and you treat these outputs as class scores. Then you pass it through a softmax function to interpret it as class probabilities, and then you compute, for example, a cross entropy loss, which will try to get your probability vector close to a singleton distribution vector. Well, all the probabilities on the correct class, and then you take that and you back propagate from there, from this kind of loss, backwards. So that's what we saw until now. Now, let's talk about image classification. So why not use MLPs for images? Okay. So as you can see, each layer is fully connected to the previous layer. Okay, each neuron here has to be connected to every single output of the previous layer. So we have a problem with number of parameters. It really increases very, very, very quickly. So if you take just a very, very small MNIST image, as you saw, for example, in the assignment, then you have 784 weights per neuron. And if you take a less trivial image, then you can have potentially millions of weights just for a single neuron in a single layer, just because of these full connections. So if you try to stack layers, it quickly gets out of hand in terms of number of parameters, and the projector is not very good, but okay, so what's the problem with lots of parameters? Okay, so again, this is a reminder from the lecture. It greatly increases the risk of overfitting. So for example, here is an MLP with 1 hidden layer, 3, 6, and 20 neurons. You can see how strongly this becomes overfitted to. This is the decision boundaries two classes, okay? And this is the this is more hidden layers with the same number of neurons. So it's the same idea that you increase the number of parameters, you get more of a fitting. And also another problem for images is that the fully connected layers are sensitive to translation. For example, if you connect this neuron to all the pixels, and then you learn how to classify MNIST. So you have for example the digit 9. Okay, so some neuron will probably learn that the digit 9 has to have some kind of vertical line here. But if you take this image and then you turn it into like a translated image where the 9 is a little on the side, in the side of the image, then the neurons that fired for this vertical line will no longer fire because these full connections. The neurons that previously were connected here are now not connected. So the problem is the fully connected layers are sensitive to translation, while actually images are not, because we want to classify a 9. It doesn't matter if it's where it is in the image, we still want to treat it and understand it. Okay, but we still want to use deep neural networks because we can learn hierarchical features from the data because of their strong representative power. So we will use convolutional layers instead of fully connected layers. So now let's talk about that. Okay, let's start with the structure of a convolutional layer. Again, unfortunately, the colors are not very good here. It was much more colorful. You can see it on the online if you want. Okay, so let's start structurally before we go into what a convolution is and stuff like that. Just structurally, a convolution layer is kind of similar to this idea of multiple neurons that are connected somehow to the input and produce some kind of output, but with some key distinctions. So first of all, a neuron is only connected to a small region of the previous layer. It's not connected, if the previous layer is an image, it's not connected to the whole image, it's connected to some kind of local region. Instead of a 1D grid like in the MLP, they are stacked in a 3D grid, okay? And if there's a row of neurons in the same depth, here I used colors to represent the depth, then they have the same parameters. So for example, these neurons all have the same parameters, and these have the same parameters, and these have the same parameters. And these neurons, this is the same color. It's hard to see it, but this whole last slice of depth has neurons with the same parameter. Each neuron here is connected to a different region in the input. Okay? So now, after again, keeping with the structural kind of idea, the important thing to understand is, first of all, they operate and produce volumes, okay, which means 3D tensors. If you think about this input as an image, then it has 3 color channels and some kind of height and width. So it's indeed a 3D tensor. And they operate on that, and they produce that, because you have, for each neuron here, 1 activation. Okay, so if you think about it as structured like that, then you'll get an output volume. So this is a volume of activations, and this is another volume of activations. That's another volume of activations. Okay, so another very important thing to remember. Each neuron here is spatially local, but it operates on the full depth dimension of its input volume. Okay, so here let's look at these 5 neurons that are in different depth slices here. Okay, so all of them, because they're in the same spatial location but in different depth, the fact that they're in the same spatial locations mean that they're looking at the same spatial region in the input. But crucially, all of them are looking at all 3 channels. So they're not looking at the whole input. They're just looking at, for example, on a 3x3 window, but they're all looking at the 3 channels. Okay, so this one, they're all looking at the same slice, but they have different parameters. That's why they have different colors here. So that's the kind of the structural composition of convolutional networks. Now let's interpret it as actual filters that do convolutions. Okay, so let's start with the bottom image here. The interpretation as a filter is this. If you for example think about this image, this is I guess a 28 by 28 image. This is a 3x3 filter, which has some kind of diagonal line. Okay, so imagine that you slide slide this filter over the image, okay, and you compute dot products. So it's like at each point, it's a dot product that tells you how much this filter is correlated with what it sees with the image. So this will highlight diagonal edges. That's why it highlights this diagonal edge here and this diagonal edge here. Highlight means it will respond. It will the dot product will be higher. Okay, so now back to our structure of convolutional layers. So if this is my input volume, and I want to think about it again, since each depth slice has the same parameters and it's looking at different regions. Each neuron is looking at different regions. I can think about each parameterization as a filter. Okay, so here the filters, as you can see, they're 3 by 3 by 3. They're cubes. Okay, because they have to look at the depth, and they're 3 by 3 because that's the spatial size of the filter. So here's one filter. I'm going to slide it over my input volume. Okay, sliding it, and each time I slide it, I get one number because it's a dot product. So that's why this slice here of the output volume, okay, is composed of the results of this filter with this input. Okay, so each one of my filters produces one slice of output volume depth. Yes.
Filter is not activated.
Well, when I showed before the structural interpretation, you can think about it as if there are lots of neurons that each neuron is connected to a different region. This interpretation, just forget neurons for a second, okay? You have 6 filters. Each filter is 3 by 3 by 3. Okay, and you're sliding them on your input volume and creating these kind of depth slices. Okay, so it's like 2 ways to think about it. I started with the structural way, and this is like the convolutional way. Okay, clear? Okay, so for each convolutional layer, we have multiple kind of filters or kernels, convolutional kernels. Each 2D slice is known as a feature map. Okay, each 2D slice here is known as either a feature map or a channel in the output or input. Okay, so each convolutional layer, again, each convolutional layer has multiple filters. Each filter creates a feature map because it operates on the whole input, creates one slice of output. Okay, so convolutional layers have hyperparameters that allow us to kind of define how they operate on the data, how they work. So let's assume that our input volume has shape C in, H in, W in. So this is the number of channels, height and width. This is the order I'm specifying it because, as you will see in the PyTorch documentation that you'll probably have to use a lot or have already used a lot, then this is the kind of standard order of how you specify input for conv layers and also the output. So so for example, if you have a regular image, it might be like three color channels and I don't know 1,000 by 1,000. Okay, so that's input shape. So to define a conv layer, you have to specify some hyperparameters. First of all, the number of convolution kernels or filters. Okay, like I said, there's more than one filter. The size of each filter. In the previous image you saw there were 6 filters, 3 by 3. So the spatial extent, how large the filter is in the spatial dimension, not the depth dimension. The stride is how I'm jumping the filter. I can jump it 1 pixel at a time, or I can move it larger. I'll show you very soon a visualization of that. And whether or not I'm padding my input, and parameter called the dilation, which is how I'm applying my filter to my input. I'm not really going to talk about it. This relates to what Alex was talking about previously with dilated convolutions. I'm showing it here for completeness, but we don't have really a lot of time to talk about that. Sorry? Yeah, per conv layer, you have all these parameters to define. And they influence the output shape. So here, unfortunately, this is not green. It's supposed to be green. Okay? So imagine imagine the top part is green, okay? So let's look first of all at this left example. Here we have no padding, a stride of 1, and a dilation of 1. Let's ignore the dilation for now. So the shaded part is our filter. The blue bottom part is the input. and the top is the output. So as you can see, the filter is sliding 1 pixel at a time over the input, computing a dot product. Each dot product gives you one number of the output, okay? Here, padding is 1, so we're adding zeros around the input. Okay, stride is still 1, so we're jumping our filter 1 pixel at a time. But this gives us an input of the same size, an output of the same size as the input because of the padding. We have more places to put our filter. Okay, here the stride is 2. It means we're jumping our filter 2 pixels at a time. So this compared to that, we get a smaller output because we're jumping. So we have less dot products. And this is what dilation looks like. It basically means you're applying the same number of filter parameters, but to a larger part of the input. Okay, so importantly, the second combination, there are combinations that you can use of filter size, padding, and stride that preserve dimensions. So there are specific combinations that allow you to preserve, and other combinations allow you to shrink your dimensions. Okay, so briefly, if you have a set of hyperparameters, then your output will have dimensions that are specified by the hyperparameters. Note that each convolutional kernel in your conv layer will be of this shape. Okay, so you defined f. For example, you want 5 by 5 filters, but the actual filter size will be Cin, which is the depth of the input, 5 by 5. Okay, so because each layer operates on the whole depth, as you saw before in the structural part, I showed you that each filter operates on the whole depth. So these are the filters that you're going to get with the parameterization that I showed you. And the output volume is specified by this kind of annoying formula. But let's ignore, for example, the dilation. Let's say just it's 1. So you can get a much nicer formula, something like this. H out should be H in 2 padding minus filter size over the stride. Okay, floor plus 1. Hope you can see that. So this is a much nicer. This is like you can actually use this form more easily. Usually you ignore dilation. You can see, for example, it makes sense. If you take a stride of 2, it will tend to shrink your output by a factor of 2. Okay. If you pad, it increases your output. If you increase the filter size, it has more place. If you increase the filter size, it has less places to be in. So again, your output will shrink. Okay, so this kind of makes sense. You can play with it and prove it to yourself. And so these are the height and width of the output volume, and the depth of the output volume is just determined by the number of filters you selected. So you say you want a convolutional layer with 10 filters, and you get an output of volume 10, of depth 10, okay? So anyone want to try to guess how many parameters are in a conv layer? Okay. Times f times f times k. Okay, almost. Remember that it's an affine transform. Yeah, exactly. So so this is the number of filters. This is the dimension of each filter, and you need a bias term. So it's an affine transform. Okay. So nice. Okay. This is the number of parameters in the layer. As you can see, it's determined by your hyperparameters. Note that it's not determined by the size of the image. Okay? It's not determined by the size of the image. As opposed to what I explained before about MLPs. Why not use an MLP? Okay? So here's an example. If we have the same input image as before, we decide we want 10 convolutional kernels of size 5 by 5. This is the number of parameters we'll get in the conv layer. All right, so here's an example, a code example. I'm just loading some images from C410. Actually, I'm not going to show any images this time. We're just going to look at the shapes, okay? So we can see the volumes and understand it. Hope you can read it, because the colors are not so good. Okay, so what I'm doing here, I'm taking the first sample from the CFAR10 dataset. Okay, and when I'm doing this unsqueeze, it's just adding a dimension. Okay, so this is the actual image. it's 3 channels, okay, RGB, 32 by 32, and I have a batch dimension. That's what the unsqueeze does. It just adds a dimension in the beginning. The reason is that the norm, the expected input of all these conv layers in PyTorch is always to accept a batch, because when you implement your models, you're gonna train them using mini batches. So you'll never have one image, and if you have one image, you just have a batch size of 1. So you can think about it as like you have an image, okay? So this is your kind of 3D volume, okay? So you have a tensor containing images. Okay, so it's a 4D tensor, but let's just ignore the batch right now. I just need it because otherwise stuff won't work. Yeah.
Very by 32 by 32, you get it this way from the C file director, you switch the dimensions, because it usually specifies 32 by 32 by 32.
I applied this transform to tensor. It's a built-in transform that exists in Torch Vision. It takes a Python image library image and creates a tensor with these dimensions. That the channel is the first dimension, because that's what you need. All right. So now we have an image. Let's define 2 conv layers. So this is how you define a conv layer. It's built in the NN package. Here I'm defining a conv layer. I have to specify my input number of channels. Okay, so I'm taking the second. Actually, this is the number 3. Okay, from my image, and I just specify. I just want 10 kernels, padding of 1, kernel size of 3, stride of 1. So if you remember, this should give me an output of the same size as we saw before in the visualization. That's one conv layer. Then another conv layer. Now I'm saying I have 10 channels of input because I want to connect them. So my output channels here becomes my input channels here. I have 20 output channels just because, okay? And here I'm not using any padding, and a larger kernel with a stride of 2. So you can expect, since it's a larger kernel with a stride of 2, you can expect the output should shrink. All right, so we started with the input shape of 3 by 32 by 32. After the first conv layer, okay, we have 32 by 32 by 10. Okay, so again, the spatial dimensions did not change because of the padding and stride. I have 10 depth dimensions because I specified that I just want 10 different filters. Okay, and after I'm applying the second conv on the first conv, I have now 20 output dimensions, okay, and a smaller spatial dimension. Okay. Now, I also implemented a small function that calculates the number of parameters. You can just see it here. It just layer.parameters is just a list of tensors, and I'm just counting how many elements are in these tensors. Sorry. So 280 should make sense. Okay, if we have, let's try our formula, right? So we have 3 input channels. It's an RGB image. The first conv layer has 3 by 3 filters plus 1 bias element. So this is 28. Okay, 28, and this is multiplied by 10 because I have 10 filters. Right? So it makes sense. So I just counted them with code, and it's the same number. Okay, so important thing to note is we never specified any kind of dimensions. The number 32 did not appear here. Okay, I did not say that this conv layer should work with 32 by 32 images. So we'll see why that's important later. Okay, so now let's talk about pooling very briefly. We have pooling layers. So this is another kind of important building block in conv-nets. So it's kind of hard to see, but there are green lines here. Okay, these are green 2 by 2 lines. So the pooling layer, what it does is a layer that we use to reduce the size of the feature maps. So we have a volume, okay, a volume of outputs, and we want to reduce its spatial dimension, not its depth now. Okay, the depth we change with more convolutions. We wanna reduce its spatial dimension. So the most common way to do it is use a pooling operation, or a max pooling operation, or an average pooling operation, which basically just it breaks down each feature map. So this is a depth slice of the volume. This is one slice. it breaks it down from, in this case, 2 by 2 with a stride of 2, so they don't overlap. And from each one, it takes the max value. Okay, so you get the maximal activation from each kind of kernel here. That's why you get this map. Okay, so that's what pooling does. That's all. That's it. But why should we do that? Anyone wants to try to think why it's a good idea? Reduce the size because avoid overfitting. Okay, good. That's a great answer because it's written in my slide. Okay, good. So receptive field increases since you're kind of taking activations and shrinking and shrinking the volume. The next conv layer, which will, even if it still has just a 3 by 3 filter, effectively the output of each activation will be influenced by a larger part of the input. Okay, so the kind of the way to kind of think about what we want to do with these conv-nets is we want the first layers to learn some kind of very simple features. So the filters that we're going to learn, remember that these filters are learned, yeah? Okay, I didn't say that previously, but the idea is to learn the filters. So the filters represent features. We're trying to learn features from the data. So we want to learn, for example, that detecting diagonal lines is important. So we detect diagonal lines, and then we want the consecutive deeper layers to start combining, using the convolutions to combine the features, and then find more interesting features. So you can start with just simple features, and then somewhere in the deep net you have neurons that fire if they see a cat's eye, okay, or cat's ear, because they're composed of multiple layers that each detected simpler and simpler and simpler features. Okay, so quickly in code. So you have like a conv layer, you have a max pool layer. This is what I showed before, kernel size 2, stride of 2. This is the output of our previous conv, 20, depth, 14 by 14. After max pool, you can see depth doesn't change, okay, because it operates on each slice individually, but we have a factor 2 downsample. All right, so let's talk about networks now. So another thing I didn't say until now is activation functions. What I showed you basically is that we're doing a convolution, but that's a linear operation, okay? So we're just applying some kind of linear filter. Each depth slice is a result of a different filter, but everything is still linear. So if we just stack layers like that, we'll just get a linear network, so it doesn't help us a lot. So we have some kind of nonlinearity. Usually in conv-nets you use ReLU. Okay, if you remember what ReLU is, it's a function that looks like it's 0 here, and then it has just a slope of 1. Okay, that's rectified linear unit. And a reason to use that is it helps with vanishing gradients, but I'm not going to go into that. Just remember that you need some kind of nonlinearity, obviously, as in any deep network. So here we're going to use ReLU. And we have to, after some convs, do some pooling to decrease the spatial dimensions and help us learn hierarchical features. Okay, and at the end, we want to take all the features that we learned, because think about it, like in the end of the network, you have all of these features, like one of the features was the cat's ear, and one of them was the cat's nose, and one of them was the cat's eye. So we want to combine these features to some kind of classifier that will tell us if actually we're seeing a cat, or the feature that detects eyes is very low right now, so it doesn't detect anything. So we need some, if we want to do classification, we should combine the features with a fully connected layer and add a softmax. So let's just look at a diagram here. So this is like a general kind of diagram of the general idea of most architectures. Is just you have these repeating blocks of some number of convolutions, and then a pooling layer, and then more convolutions, and then a pooling layer. Okay, after each convolution you do a ReLU. Sometimes you add extra stuff like batch norm. But the idea is that you're trying to learn these hierarchical features. So you're repeating these stacks of convolutions and pooling, and then in the end you do one or more fully connected layers with the softmax. That's a general idea. Okay, so of course, there are lots of details to consider when you want to kind of think about an architecture. You have to think about the size of the kernels, the number of consecutive convolutions. You want one convolution, you want two after the other. If you kind of think about it a little, then when you stack convolutions, because of the nonlinearity, you get more representative power. Okay, so you can stack them. You can use batch normalization, which is mostly used, or dropout to improve generalization. And you can think about maybe you don't want fully connected. We'll see that soon. And also skip connections. We'll see that soon. So the bottom 2 points, we're going to see it now in the next. So there are a lot of different network architectures. This is supposed to be also very, very colorful. It's hard to see. So in 2002, there was a famous result of a deep convolutional network called AlexNet that won the ImageNet image classification challenge, which is a major challenge using millions of images and 1,000 classes. And it was the first time a convolutional network actually won that challenge. And since then, this is chronological order, various architectures. So since then, almost every few months, there's a new architecture that's slightly different, gets better ImageNet results. I don't know if it plateaued already, because this is from 2016, so I think maybe it plateaued. But the architectures you can see here, they differ. The size of these circles is the number of parameters. So you can see various architectures differ in the number of their parameters, their top accuracy. And you can see, for example, the highest scoring architectures don't necessarily have the most parameters right now. So there's kind of just a view. So let's kind of do an example in PyTorch how to implement a very simple architecture. We're going to implement ResNets. Okay, so it's an architecture from '98 by Yann LeCun, which is one of the fathers of deep learning, and he used it for classifying digits. Again, MNIST. So this guy, he tried every single conceivable machine learning algorithm on MNIST. So one of them worked really well, and it was this network. So it's drawn a bit differently than what I showed you before, but it's the same kind of structure. You have an input. This is the volume. It has 6 feature maps, so 6 filters. Okay, the dimensions change, so that means he doesn't use padding or strides. Then he subsamples it with pooling. Then another conv layer, 16 filters this time. Again, the dimensions change. And then another pooling, and then 3 fully connected layers. The last one with 10 outputs, because we want to classify digits. So let's implement that in PyTorch. This is ResNets, which I implemented for you. Hope it's large enough to read. Okay. So I split my implementation to 2 parts here. I have the feature extractor part and the classifier part. So the feature extractor part is the part of the neural network that creates our feature maps. Okay. So in the end, you can think about the last convolution layer's output as a bunch of features that were learned from the data, and this is how we're going to classify our images. Okay. So this sequential here is a bunch of convolutions that will calculate our features. So let's just break it down. Let's say we have 3 input channels because it's a color image, okay, and we have 6 output channels because that's the architecture. 5 by 5 filters. Again, these are just from the architecture. We have a ReLU, we have pooling, factor 2, and then another convolution from 6 input channels to 16 output channels. Again, 5 by 5. Another ReLU, and another max pool. This is our feature extractor. If you look at the diagram before, you'll see that it matches. And then our classifier, remember we had 3 fully connected layers. So first fully connected layer, okay? Now the input features, okay, remember that this fully connected layer is looking at the volume. We need to take our volume and squash it to a vector and then connect every single neuron in our fully connected layer to every single output in the volume, right? So the number of outputs in that volume is this, okay, 16 by 5 by 5. You can see it in the diagram. This is the output. dimensions. Okay, we have 16 feature maps, and the spatial dimension is 5 by 5. And then we have a nonlinearity, and then another fully connected layer that takes it from 120 output features to 84, and then from 84 to 10. This is the architecture. Okay. Now our forward function, which this is what we apply to the data, it applies the sequence of feature extractions on our input, gets the features, takes the features, squashes them to a single column vector, a row vector, sorry. This is the batch dimension. Again, okay, so this will just be 1 because we have one sample in our batch. So it'll be one sample and then a long vector. And then it takes our classifier sequence and gives it that vector. Then we get the class scores. Okay, is that clear? Okay. So LeNet, you can see that if you kind of print the network, then PyTorch gives you like a nice summary of what it contains, like a feature extractor block and all the convolutions with all the sizes, helps for debugging. Basically, I ran my C410 image through LeNet. I got a tensor of 10 elements, which is my 10 class scores. Okay. So now let's talk about fully convolutional networks. So I have a question for you. We didn't. Yeah.
Is there a built-in function in PyTorch for gradient?
Yeah, of course. You have automatic differentiation of everything. After you have your network output, you compute the loss, for example, cross entropy, and then you just use the backward function, which is built in, because all these operations record what their gradients are, and then it goes back through your computation graph and gives you the gradient for each of your parameter tensors. So you have, in the case of convolutional networks, you have all these filters that they have gradients. You have to implement the optimizer. You have to take the gradient and add it with a learning rate. You have to learning rate times the gradient, add that to the weights. No, you have also that built in if you use the optimizer. You're gonna see that. Okay, so the question is, we never specified an input image size when implementing the network. It was never specified anywhere. So can we use this network on images of any size? What do you think? It's not a theoretical question. I mean, I have an implementation. If I give it an image of size, I don't know, 1,000 by 1,000, will it work or not? Okay, why not? Why yes? I didn't specify the input size anywhere. I had 3 by 32. I specified the number of input channels, and after that, the number of channels was 3, then 6, then 16, I think. No, so okay, exactly. So when I squashed the output volume to a vector and applied the fully connected layer, then it mattered. Okay, then it mattered because the fully connected layer needs to be connected to everything. So the answer is no. Okay, let's try. Here I have a larger image. It's 3 by 64 by 64. And I'm running it, so hopefully, okay. So this is an error, size mismatch. When you see these kinds of errors in your models, you're going to have to debug it, understand where's your problem. It means you didn't build your model correctly. Okay? Doesn't work because of the fully connected layers. But let's say we want to make it work. So it's kind of annoying that our network is supposed to learn translation invariant stuff, like supposed to represent a 9, but we can't use it on a larger image. I mean, if I take this 9 and just, I don't know, embed it in a larger image, I want it to keep working. Okay. So what can we do? We can replace the fully connected layers with other convolutions. Okay, so before I'm going to show you that, I'll try to explain it. Explain how to do that. Remember that you have an output volume. Okay, you need to connect to every single. This is your output volume. You need to connect to every single point in the output volume. So we squashed it and we created a fully connected layer. Okay, but so. Let's say it's let's say it's, our output volume right now after LeNet is 5 by 5 by 16. 16 is the depth. Okay? So how can we convert it to fully connected? The answer is, first of all, if you look at this volume, let's take a filter that covers the whole space. Okay? Let's take a 5 by 5 filter. Okay? And apply it. Okay? So I will basically combine every single element here, and then I take multiple such filters. Remember that I wanted my fully connected layer to produce 120 outputs here. I wanted to take this volume, okay? I wanted to squash it and create 120 outputs. So if I just take 120 filters that span the whole space, that's what I'll get, okay? So let's see how it's done. I'll try to increase the font a little. Okay, remember, so we had the last feature map, 16 depth, 5 by 5. So let's replace our classifier from LeNet. This is the same LeNet, but I'm just overriding the init and changing the classifier now. The classifier will be convolutional layer with 16 input channels, 120 output channels, because that's what the architecture wants, and 5 by 5 because that's the shape of, at least of my original data. And I'm not using any padding or stride. I want the filter to just kind of cover the whole spatial section. Okay, I'm doing that. And then I'm doing something strange here. Okay, remember the fully connected layer was 120, then another fully connected layer to 84, then another fully connected layer to 10 classes. So how do you do that with convolutional layers? Okay, you take a 1 by 1 filter. Okay, think about it. It's kind of strange because if you think about convolutions from image processing or signal processing, it doesn't make sense to use 1 by 1 anything because it would just multiply your signal. But here, remember that you have the depth dimension. So it's actually 1 by 1 by 120. Okay? So if I have 84 filters of shape 1 by 1 by 120, then it's basically implementing the same thing. It will just have different shapes. Okay? If I draw it, then let's say this is my input volume. I can define a filter that looks like that, 1 by 1, and it will go all the way back, okay, until the end of my depth, and do a dot product. Okay? And this will give me one activation. So if I have lots of these kind of filters, I will get lots of activations. I want 84 activations. That's what I'm going to get. Okay. So this is my fully convolutional LeNet. Let's print it. You can see the classifier part now is fully conv. Okay, so let's take the image and forward it to the network and see what we get. So this is our the first image, the regular size. It was 32 by 32. Remember, I got now this shape. I got depth of 10 and spatial dimensions 1 by 1. Okay, so remember we have 10 classes. So it just basically, I got the same 10 class scores, but in a different shape. But now when I give it the large image, which is twice the size, I got this shape. So can anyone think what's the meaning of this output now? So now, again, first I showed you that the network did not work on the larger image. Now I showed you after making it fully conv, it does work on the output, on the larger image, but I get this shape. So what does it mean? Remember, this is the width and height. Any ideas? Okay. Okay, good. So basically what he's saying, I think, is that you get 10 class scores at different locations in the image. You can interpret that as a heat map. Okay, you can interpret it as a heat map. So for example, if we trained on images like that, we had a fully connected layer at the end, and we got a vector of scores, so the score for the cat was high. Now we take a larger image with a cat. We do the fully conv thing, okay? And now we have you can think about like taking your conv layer and sliding it over. You're turning the whole layer into a filter. You can slide it over. And at no. You have to calculate the dimensions. So if you want to understand why it's 9, okay, you need to I calculate it. It makes sense, but you have to calculate it using the formulas from before. So the idea is you slide your filters over the image, and at each point you get 10 numbers, which are the class probabilities or the class scores at least. Okay. Now So this would be a volume, but now we're just looking at one of the scores, the score for cat. So you have now a 2D image, and you can interpret it as the heat map for where the cat is. Okay, so now we took our layer, our network, we created a fully conv network, and it allows us to basically slide our filters over larger images. It won't work for smaller images that we train. No, you get this is actually a volume. It would hopefully show some heat here and very low values here. It depends. I mean, you can if you classified only dogs and cats and you give it an image of a mouse, then who knows? It might decide it's a cat. Okay, I'll explain it. I get your question. In the original Linet, when we used the original image size, we got 5 by 5. Okay, but now think that you're inputting a much larger image, and you have the same downsample operations. So this volume will not be 5 by 5 anymore. It will be something else larger. Okay, and then and when I created the conv layer, I said I want 5 by 5 to start converting it. Yeah, I hard coded it for the original input size, but it allows me to take larger images, okay, and kind of compute the heat maps, because it's for larger images I take this last 5 by 5 and slide it over the volume that I got. So this is the last part of the tutorial, residual networks. I hope we're gonna get over it. If we don't have a chance to go into the code, then just download the notebook and kind of read it yourself. It should be easy to understand, hopefully. So we want to learn. We say that deeper is better because we want to learn more complex features that are functions of the more simple features. So we want more depth in our networks, but the problem is that when we add depth, we have various kinds of problems, like the vanishing gradient problem. We have different convergence. It causes all our gradients to be 0, so our network does not converge, because if all the gradients are 0, then the parameters do not change. And since we have much more parameters when we add depth, then it's a more difficult optimization problem. Our parameter space increases, might be even more non-convex, okay? So it's harder to optimize. But if you think about it, if you take some kind of deep network and add another layer, in theory, you should not get any less accuracy, okay? Because the way to think about it is you can construct a network that's one layer deeper. It does an identity map in the end, okay? And it should give you the same accuracy. If your previous network was good and you have an identity map at the end, you should get at least the same accuracy. But in practice, that's not what you get. You can see that even for training errors, okay, so it's not a question of overfitting. Even for training errors, you get some kind of degradation if you just kind of stack more and more convolutional layers one over the other. So this is a 56-layer network and a 20-layer network. The training error is higher. So it's not an issue of overfitting with more parameters. It's actually not working for the training. Okay, so it means that for some reason the optimizer, even though we know that there exists a solution that should be as good, just by adding one more layer, it should be as good. So there should be at least a solution. I can't find it with my optimizer. That's what I'm saying. That's the kind of idea behind ResNets. So they attempt to address this issue by building a network that includes shortcut or skip connections. So these are conv layers. So you have like conv batch norm relu, conv batch norm relu, and after each two convolutions, you do this kind of identity map. You skip, okay, and then you apply the relu after the combination here. These are usually just 1 by 1 or 3 by 3 convolutions, followed by batch norm. And the idea is that this really helps tackle some of the problems of depth. It's easier to see that this helps with gradients. So at least from this branch, the gradient can flow more freely. Even if your gradients start getting very, very weak, you can still pass them here, and they kind of some of the gradients will reach the start network, the start layers. Okay. And another kind of insight here is that instead of learning a new mapping that transforms the previous to the next, you're taking the previous, and then you're just adding what to add to it. You're learning some kind of delta to add to what you had before. So this kind of makes sense if you think about what I said about identity mapping. So it's like there should be an identity mapping that will give you the same results. If you just learn some kind of small delta that you can add over that, it should be easier for the optimizer because it can always just drive this to 0. It can always say that the delta should be 0, and at least we'll have an identity map. Okay, so it should help with learning depth. It should help the optimizer optimize. That's kind of the intuition behind the ResNets. So I'm kind of out of time. I'm just going to show you what I have here. This is from the paper, from the ResNet paper from 2015. This is the most simple ResNet, 18-layer ResNet. It has kind of for all configurations, 7x7 64 conv, then max pooling, and then they have this repeating structure of 2 times the basic block that you saw before. So you just take this and repeat it lots of times, but with different depth dimensions. Okay, so here you have 64 filters, and then 128 filters, then 256, 512. Okay, so you kind of repeat it, the same structure, repeat it, and at the end, average pooling, fully connected, and softmax, as we discussed before. So I'm not going to go into the implementation, but it's a pretty simple implementation. I implemented for you the basic block as a different module, okay, with the shortcut connection. There's a kind of a twist here that sometimes you have to adjust the size of the shortcut because the output dimension is not like the input dimension, so it's not exactly an identity map. But this is what also they do in the paper. And after you have this building block, then you just create a layer, the ResNet model. What it does is that it uses that building block. Here I took groups of 2 building blocks in a sequential. And I just kind of automated the whole thing to create the output channels. So just kind of read it, and you'll get the idea of how to create the architecture from the PyTorch building blocks. Okay. So yeah. Okay. So thanks.